Hi, and good afternoon, or actually good morning. Today, I would like to talk about superposition of waves. So in the last chapter, we talked about waves. In particular, it was traveling waves. And it was just one wave traveling on its own. Now, what if one wave meets another wave? What if you have more than one wave? What if you have two waves? What if you have three or four? What happens? What happens to the wave function, that the displacement, d? Well, when you have more than one wave, then you add up the waves together. But then the displacement is a sine and a cosine function. So you end up adding sines and cosines, and you can imagine when you add sines and cosines, you have different identities that you will use, and interesting things happen. So I have this demonstration table here, or the demonstration equipment here. So let me just tell you what I have. I have this thing here that generates functions, all right? It generates things that, it makes this thing here go up and down. Let me just show you how it works. So it makes it go up and down. I can make it go up and down faster, and pretty much as fast as I would like. So now it's shaking once a second, twice a second, 3 times a second, 4 times a second, 5 times a second, so on and so forth. That's called the frequency. I have here let me put it on standby mode. I will show you this because we need to see the numbers in a little bit later. Actually, when I show you what the lab is about. I have here 2 kilograms. The 2 kilograms, the only function they have is to just keep this from sliding on the table. There's not much friction, and when the thing starts shaking, it starts to move, and I don't want it to move because I would like the string to be to keep the same length, to stay the same. The distance from here to here, I would like it to stay the same. I have a horizontal string of a certain mass per unit of length, and to create tension, I have a 200-gram mass here, and I put it on here. So the tension on the string, since the mass, when the string is shaking, the mass is at rest, basically, then the tension upward must equal to the mg downward, so that tells me what the tension is. Now, let me move this a little bit. As I start sending waves, so the thing shakes the string once, the wave travels, it gets to here. Gets to here, and then it stops. It tries to lift here, but it's pinned. So let's assume this is pinned. So when the wave is traveling, so when it gets here, it applies a force. It tries to lift here. Well, when it applies a force here, a force is applied back onto it, downward. So this thing here now creates a wave that's downward. By the time this one creates a wave downward, the other one has sent another one. And if we send them just right, the wave downward from here plus the wave that's coming in upward, it would be just the right time that they cancel at this moment. And then interesting things happen. We create what's called standing waves, meaning you would have what's called a node here because this point would not move. You would have another node here, and so on. Depends on how fast you shake it. Or you can just have a node here, and basically a node here, and then maybe something in the middle. So let me just show you what happens. So here, let me just look on the camera if it's clear or not. I don't know if you can see the numbers. Let me zoom, let me get closer. So it says 1. In here, it should say, you should see it. It just says 1. Let me get here. Hopefully we can see it. Okay. Much better. Yeah. So it is 1 hertz. Let me take it off the standby mode. And let me just go to about 8. I can change this to like 8.1. See, if you shake it by hand, you will get the same effect, but you cannot control how quick you can shake with your hand, not very accurately at least. So at about 8.4 hertz or 8.5, it is shaking as one piece, about. It's not very clear. Let's see what we get when we shake it in two pieces. Let me go to about 16 or 17. Yeah, let me go to 17. Here, 17 and a half. I think it's very clear that it is shaking in two pieces here. So we have a node here because it doesn't move. We have a node here because it doesn't move that point, right? And we have a node here over here. And the things that shake the most in the middle here that have the maximum displacement, they're called antinodes. Let me do, the next one will be around 25 or so. Let's zoom in to it kind of slowly. And we'll collect data when we do the lab. All right, so I think that's 3, fairly clear. Yeah, that's 3 at about 27.4 hertz. Okay, so let me put it on standby and go back to the chalkboard and see what's happening. All right, we're back to the chalkboard, and the chapter title is the superposition, meaning you superimpose things on top of each other. You add things. Like combinations of different wavelengths, of different waves. I've here the identity sign of alpha plus beta equals sine alpha cosine beta plus or minus cosine alpha plus sine beta. And the cosine of alpha plus or minus beta would be the cosine alpha cosine beta minus plus the sine alpha sine beta. Okay. So I would like to show you now. So we said we will send a wave. Here is the wave. We're going to send it. It has a certain amplitude. Here's the x-axis. And we're going to send it to the right. And this is the amplitude of the wave, d. And remember, d was given by like the amplitude times the sine of kx minus omega times t. And this is a wave that is traveling to the right. Now it gets to, let me just draw this part here. It gets to the wall, to that end, to the end here. And this wave pulls down on the wall, so the wall pulls up on the wave, and so it will send a different wave to the left, And so let's just consider wave 1 that is traveling to the right, and wave 2 that's exactly like it, but it is traveling to the left. Let me call it D2. It's exactly like it. Same amplitude, same frequency, same wavelength. But it's traveling to the left. See the plus sign here. And remember what K was. K was equal to the 2 pi over the wavelength, and 2 pi the wavelength, and omega was 2 pi over the period. Okay, 2 pi over the period. I wish to add these two waves. So before I do that, I'm going to split the sign into a sine and a cosine using this identity here. I would use the identity with the minus sign, so I would have a minus sign in the middle there. So I would have a sine of kx times the cosine of omega t, and then minus a times the cosine of kx, and then the sine of omega t. And I'm going to do the same thing here. I have a, the sine of kx, cosine of omega t, and then plus because there is a plus sign here, the cosine of kx times the sine of omega t. And now let's see what we get when we add both of them. When we have this new wave, d, which is d1 plus d2. What do we get when we add them? Well, you see this term and this term, they're exactly the same, but one is negative and one is positive, so they cancel. These two terms here are exactly the same, so they add. So we just have twice a times the sine of kx times the cosine of omega times t. So now, this is a wave, and it has this new amplitude, which we can call a of x. The amplitude, the new amplitude is a function of x. You can just call it d is this new amplitude, which is a function of x, times the cosine of omega times t. And so, and this a of x, which is a as a function of x, is equal to twice a times the sine of omega, the sine of kx. Now, what are the properties of this wave? Well, this wave is 0 whenever kx is equal to 2 pi. Right? It's 0 whenever, actually whenever it's equal to a multiple of pi. So if you were to plot it as a function of x, you would have this. You would have the wave simply doing like this at time t equal to 0. And then when cosine is equal to -1, the wave will sometimes look like that. And everything in between, sometimes it will only have this amplitude. Sometimes it will have a negative amplitude here. All right? What's important is you have these nodes. This is called a node. A node. This is another node. And the distance between nodes is half a wavelength. This is a node. That's also a node. That's a node. And these things that have maximum displacement from them, node, by the way, sometimes they just name it capital N, and this is called an antinode. Antinode, or antinode, and it's symbolized with the symbol capital A. And it creates what's called a standing wave. So it's traveling waves, but they combine to give you what seems to just be a wave that's just sitting there. It's not really sitting there. These points always are 0, but they change their amplitude as a function of time, or as a function of x also. Okay? And so that's that. So I mentioned, when is this 0? Well, it's 0 when this is not 0, the 2 is not 0, and the amplitude is not 0, so it's whenever this is 0. So this a of x is equal to 0. When is it 0? When kx is a multiple of pi, is equal to n times pi. Because if kx is equal to pi, or negative pi, or 0, or 3 pi, or 4 pi, or 5 pi, or negative 5 pi, you get this. And so it's 0 whenever n pi, whenever x is equal to n pi over k. But k is 2 pi over lambda. So if I replace this by n pi over 2 pi over lambda, so the lambda goes up. So I get it's 0 when x is equal to 1/2 of n times lambda. And this number n here, again, it's a pi or a 0 or negative pi. It's an integer. It's 0 plus or minus 1, plus or minus 2, and so on. That's when this is 0. So the spacing between two adjacent nodes is half a wavelength. Because the first node, let's say, is at x equal to 0, when n is 0. The next one will be when n is 1, and so that's half a wavelength. So adjacent nodes are separated by half a wavelength. I want to show you an example here. So the example says the following. You have a very long string. It has a linear density of 5 grams per meter, is stretched under tension of 8 newtons. So we have a string under tension where mu is 5 grams per meter, and that's 5 times 10 to the minus 3 kilograms per meter. We have the tension, it's under tension, and the tension is 8 newtons. They say they're sending waves of 100 hertz, so the frequency is 100 hertz, and the amplitude of the waves, they're telling us, it is 2 millimeters. 2 millimeters. The waves are 2 millimeters. And so the question is, what is the node spacing? What's the spacing between two adjacent nodes? And then what is the maximum displacement of the string? What's the maximum displacement of the string? So we're sending those waves like this. They have this amplitude. So imagine you have wave 1, it has this amplitude. Wave 2 has this amplitude. And so they generate standing waves. So D1 and D2. Each of them has this amplitude. So the maximum amplitude is the 2A, is what's in front here. So that's the maximum amplitude. And then what is the speed of the waves? First of all, let's find the speed of the waves. Well, V, as usual, is the square root of tension over mu. And so that's 8 over 5 times 10 to the 8 newtons divided by 5 times 10 to the minus 3. So 10 to the minus 3 on the bottom. You take the square root. Let us get the speed of these waves. You have 8 divided by 5 and times 1,000. So that's 1,600 to the 1/2. So that's 40 meters per second. I know that lambda, the speed v is equal to lambda times the frequency, and so lambda will be v over f. And the frequency is, I think we said 100 hertz. I just wrote hertz. Excuse me. It was 100 hertz. Yeah, 100. This should say 100 here. 100. So I have 40 over 100. So that's 0.4 meters. So what's the distance between nodes? Between adjacent nodes? Well, the distance between adjacent nodes happens to be half a wavelength. So node to node distance will be 0.2 meters, half of this. And the maximum amplitude of these waves is if the two waves just add up their amplitudes, and that's 2A. The maximum amplitude will just be twice the amplitude of just of the individual wave, and that's 4 millimeters. Okay, 4 millimeters. So one way to think of it is as follows. Here's how I like to think of it. You have wave 1, and you want to add to it wave 2. Let's say they're exactly the same wave. Whatever this one is doing, that one is doing. In that case, you would just get the same wave, but twice the amplitude. It would just be twice the amplitude, right? It would just be twice the amplitude. At the highest point, it would be twice. But it vanishes wherever both of them vanish, because 0 plus 0, they give you 0. And in between, you get the amplitudes. On the other hand, if you get the first wave looks, let's say, like this, and the second wave looks exactly opposite to it, in that case, you will just get nothing. You will get 0. You get 0. That's called superposition of waves, adding waves. All right. So next, I want to talk about standing waves on a string, on a particular string. So let me just draw for you a string, and our string will have length L, and it will be under tension mu, and it has a linear density mu. All right, linear density mu. Okay, and so let's see what can the string do. So here's our string. It's confined in here. So standing waves on a string. So the string is of length L. It's pinned here, so that's a node, and this is another node. And the string is of length L. And if it's a standing wave, then the string can shake in one piece. The next one will be for the string to shake in two pieces. So you have a node in the middle of a node, a node, a node. And then, by the way, this is the antinode. That's your antinode. That's your antinode. And you can do in two pieces, in three different pieces here. You can have something like this. You have your node, 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 node. You will have here an antinode, an antinode, and an antinode. So that's that. So let's take the first case, first one. See the first one here. In the first one, how long is the wavelength? Well, from here to here is L, and this is just half a wave. That's half a wavelength. The other half would be here, but you have a wall here. You have two walls. It's confined. So the full wavelength will be twice the length. And I'm going to call this one here lambda 1. Lambda, because it's the first one there. So I conclude that lambda 1 will equal to twice L, which is to say 2L divided by 1, by the number 1. And so the frequency, because the speed of the wave is defined, is given by the tension, square root of tension over mu. That's set. That cannot be changed. It is the wavelength gets shorter, the frequency gets higher, the frequency gets lower, the wavelength gets longer. So the combination of lambda 1 times f1, I'm labeling 1 here, meaning when the string is shaken as one piece. And that's equal to the speed of the wave, which is the square root of tension over mu. And I get f1 will be v divided by lambda 1, which is equal to v divided by 2L. All right, let's get the second one and see what we have. For the second one, let me call it lambda 2, this one. So this is one wavelength. I fit an entire wavelength within a length L, so the wavelength itself, lambda, will equal to L. This is the same as 2L divided by 2. You see, lambda 1 was 2L over 1, lambda 2 is 2L over 2, and we will see that this will go on. And that means that lambda 2, f2, which is equal to v, so you get f2 will equal to v over lambda 2, which is equal to L, So this is f2. Notice, f1 is half of v over L. f2 is v over L, so it's equal to twice of f1. And notice here, lambda 2 will equal to lambda 1 divided by 2. Right? Because lambda 1 is 2L, so it's 2L over 2. Yeah. And then for the third one, lambda 3, let's see. We have half a wavelength, plus half a wavelength, plus half a wavelength. That's 3/2 of a wavelength fit within a length L. So 3/2 of a wavelength will equal to L. So 3/2 of this lambda 3 that I'm calling will equal to just L. So lambda 3 will equal to 2L divided by 3. That's equal to lambda. 2L is lambda 1, so it's lambda 1 over 3. And you can do the same logic here. Lambda 3 F3 will equal to V. And so F3 will equal to V over lambda 3. And that will give us 3V over 2L. 3V over 2L. But V over 2L is F1, so this is 3F1. So we conclude that lambda M, I'm going to label it as M, will equal to lambda 1 divided by M, right? Lambda 1 divided by M. And lambda 1 itself is lambda 1 divided by M. And lambda 1 is equal to 2L, so it's 2L divided by M. And what I mean by M here, M is just a number equal to 1 or 2 or 3 and so on. The number of antinodes, 1, 2, 3 antinodes, 1, 2, 1, or the number of segments the string is vibrating in. And Fn, or Fm, will equal to M times F1, and so that gives you just M times F1, and F1 is V over 2L. So let me just leave it like that. And M is 1, 2, 3, 4, 5, 6. Okay? And just to verify that what is lambda M times Fm, you just to check lambda M times Fm, what is this product? This times this. Well, it would be lambda 1 over M for lambda M, and then M times F1 for Fm. The M's cancel, and you just get lambda 1 F1, which is just the speed of the wave. The product of lambda and F for any M will equal to the speed of the wave. Okay, so in the next segment, I'm going to talk about standing waves as they apply to sound. So we'll have sound with like tubes, and they're open, either completely closed or open in one end or open in both ends. We'll consider all of these cases.